So again, the test will be a week from today. Usually we'll start in June. Okay? Now, if you'd like to have, the first part of Tuesday, for review questions, if you have any, I'll be glad to answer them then. Right, but unit 2 is, in my opinion, the hardest unit. As far as students tell me in feedback. So I want to spend a fair chunk of time on that. To give you guys enough time to absorb it. I'm not going to all these things really quickly, but I've been doing it for 17 years. You guys have been doing it for zero, right? So you're going to find those structures challenging. Okay. Are there any questions about that lab? Yeah.
Right lab 0. I don't know which is that one. I don't know if it's the level structures or
Dry lab 0 is if you go to file lab already to find. Can you fill it out already?
no, that's the one I'm missing because I didn't know what should I submit for that one.
Oh, scan it, all the pages, leave it on one PDF file, and then click on the assignment and it'll prompt you for a file.
The level structures?
What language?
Asking which one?
Oh, no, yeah, Blue structure.
Okay.
But you said language structure.
No.
Now, I've got a bunch of phlegm on my lungs, and it's from, I think a sinus infection with dumping fluid on my lungs. Because of that, I'm hard of hearing when I'm in perfect health. Now, I've got fluid walking my tubes in my ear, so life is great, right? Okay, so what I'm going to do now is go over a practice test from last semester or a year ago, one of the two, I forgot. Okay. The one thing I'm going to give you is that flow chart for all the reactions, okay? Now you should be using that all the time. It is a real key to reactions. Okay, so if you look at, let's see, let me pull that up. Okay, there are three parts to every reaction: reactants, conditions, products. So now, if you look at this, there's an arrow here, right? And there are arrows on here as well. So the head of the arrow is the product. The tail of the arrow is the reactants. So, for example, this guy here, or alkene here. If we want to make an alkene, we have to do the opposite of the arrow. If we're starting with an alkene, that's the tail of the arrow. So if we're starting with an alkene, we can go to a halo alkane. We can go to a haloalkane. We can also go to an alcohol, or we can go to an alkane, or we can burn it. And every one of those arrows points away from the alkene, meaning that you're starting with an alkene. Yeah. I'm sorry, what? Um, the worksheet we're working on is a practice test. I just brought this up. Yeah. Okay. Now this first problem refers to an ether. Remember, an ether is an oxygen that's got a COC connection. And it requires acid at 140 degrees temperature. Okay, so we have an alcohol. Well, that's the main. Let me go down to the reaction. Structure. Okay, so this is an ether. Oh, excuse me, this is a secondary alcohol. These are conditions. And what happens with an ether reaction is the OH attaches to another one. So remember I said the starting point, the reactants, carbon backbone is the same as the product, carbon backbone, except with ethers. With ethers, the carbon backbone is double because we're going to put two alcohols together connected with their OHs. So we are looking at that. So to name an ether, remember there's two ways. You can do the IUPAC or the common way. The common way is to look at the structure of the alcohol. Okay, this is a 1, 2, 3, 4. That's a butyl. And there are two of them, so it's a dibutyl ether. Okay, and this guy here is going to be a 2-butanol. Okay, so whenever you see an ether, make that ether, you back up to the alcohol and it's two of them. So the way I always look at ethers On either side of the O is the alcohol that created that ether. In this case, it's a secondary alcohol because the alcohol starts on a inert carbon. Now, the other way to name that, we talked about this very little, but the other way to name it, if you'd like to put some run with it, these are called a butoxy. There's methoxy, ethoxy, propoxy, butoproxy. All those are O whatever chain. So I always like the common way to name those. What's the unit on the left? And normally in our class, these are going to be the same on both sides. It doesn't have to be. It can be a methyl ethyl ether. The name, the one on this side, name on the other side, ether. I think this is a lot more simple than using the methoxys and ethoxys and all that stuff. Okay, so now it says there may be an ether. There may be a mixture. Okay, to determine that, I put on there little hints as to expect a mixture. Now, when I say expect a mixture, that means that most of the time you'll have a mixture. Sometimes if the molecules are really short, you don't have a mixture. That's the only exception. Okay, are there any questions about this guy? Yeah.
For ether, sorry.
Okay, you look at what's on the left. That comes from an alcohol. So name that as an alcohol. So it's 4-carbon backbone with an OH group on carbon number 2. Is that your question?
Yeah.
As opposed to doing that other stuff. And they're both valid most of the time, unless you're have a PhD in ethers, where you talk real fancy ethers. Most of the time people live it with a simple way. Like MEK, that's a solvent. It's methyl ethyl ketone. So instead of naming it something, hydroxyl group or whatever. Yes, please, thank you. Who's ever in last, we should just shut that door. What's today? I'm okay, does that make sense? Okay. Okay, now here we have different conditions. If we go over here to the flow chart, with 140, which is 180. So at 180, we're not forming an ether. We're forming an alkene. So 180, form an alkene, and it says expect a mixture. So let's go over here to starting point. Okay, so we've got a secondary alcohol. Now, whenever we want to form an alkene, remember alkenes are generally unstable, like my voice. So we have to put a lot of energy into that to get it to go to a more unstable state. So we're going from alcohol to alkene. We're going from stable to unstable. And remember before we started with an alkene, threw water in there, we formed an alcohol with no heat. That means with the alcohol more stable than the starting point. Here, starting with an alcohol, stable. Let's add a ton of heat with some acid. We're going to end up creating an alkene. Okay. This is going to pull off water from that alcohol. So we need to identify where the water is located. Okay. Are we having fun yet? Okay. We have to start with the alcohol. Where does it attach? What carbon? And that red dot is the carbon that's going to be part of the water we create. And the other is, well, here's an H, and here's an H. And this is where the mixture comes in. At 50%, it's going to go up to form water. 50% is going to go across to form water. Okay, so I'm just going to have a mixture. So we start with a base. And that's the same carbon as we have dotted there. So we're going to pull off water there. So we're going to end up with that plus here. So this is going to be the across this bond here. Now, which is stable between those two? Which is more stable, left or right? I don't know. In this case, you can circle either one. It's not clear cut, but there's Markovnikov's rule on looking at terminal hydrogen, or is it stability, symmetry. The symmetry, I don't know, 50-50 on symmetry. Markovnikov, we're looking at terminal hydrogen. So how many terminal hydrogens do we have on the left? Well, we have 3 here. We have 3 here. And theoretically, the hydrogens next to the double bond, we would do this here, which is 2 hydrogens. And this is 1 hydrogen. So via Markovnikov, and that's kind of a witchy one, you know. Probably wouldn't get a huge mixture one side or the other. Probably a fairly even mixture because they're very similar. There's nothing that stands out from these two. Okay. Now, this is a hint. It says oxidize and then do another oxidation. So let's go over to our flow chart. And here we are, starting with an alcohol, and we oxidize it. Okay. Now we have to determine what kind of alcohol. Primary, secondary, tertiary. Primaries give us an additional reaction. Secondary give us, we're done with one oxidation reaction. Tertiary alcohol, it doesn't oxidize. So what are we starting with over here? What kind of alcohol? Secondary, tertiary. Yeah.
Is it? Is it the third one?
Tertiary.
Yes.
Yes. You probably don't use that in common language very often. How about quaternary? Same thing, that's four. Yeah, that's a tertiary alcohol. What does that say on our flow chart? No reaction, exactly. And the reason why it's no reaction is a hydrogen disappearance is part of the oxidation process. So we don't have any carbon or hydrogens on that carbon to undergo a reaction. That's why nothing happens. Okay, so here no reaction. Here we have so this is a third degree or tertiary alcohol. This is a secondary alcohol. And if we blow this up, we have an H right there. So how many times can it undergo oxidation? How many H's are there? Once. That means it can undergo the reaction once. So once gives us a ketone. Now when we look at that carbon, there are no hydrogens left. So that's why the reaction stops. So oxidize something, and also hydrogen has to leave. Okay. And now, ketones and aldehydes are in chapter or unit 2. So you don't have to name that ketone. Or if it's aldehyde, you don't have to name it. Just put ketone down. You have to name the strength chemical though. So this is a hexanol. Okay, so we have backbone, 6-carbon backbone, and we have um, the OH groups on carbon number 2, and we have a branch. We have a methyl group on carbon number, is it carbon number 2 or is it carbon number 5? It's carbon number 5. The reason is because the backbone, if you have a functional group, the backbone takes over. And the backbone, the OH group is on carbon number what? Huh?
Is it 5 or 2?
It's 2. The reason why it's 2 is because everything except alkanes, the backbone is determined by the functional group. Ignore the branching. So the functional group is on carbon 2. So that means that is 2, regardless of kind of branching goes on. So that's why the carbon needs, or the methyl group has to be named based on the OH group. OH group is 2. So we go 2, 3, 4, 5. So it's 5 methyl. Two hexanol. Now the only time you look at the branching numbers is with alkane. Everything else, it's determined by the functional group location on the backbone. Okay, and this one here, we form an ketone and we throw in some more oxidation and then nothing happens because there's no more H's to go around. Okay. Now we're going to do this guy 2 different ways. One, we're going to spark it. What's going to happen if we spark it? Huh? Yep, it's going to burn. So whenever you see spark, burn time. Burn time always gives you carbon dioxide and water. Now, if you've got other things on there besides carbon, oxygen, and hydrogen, you'll get other things besides carbon dioxide and water. Like if we had a chlorine on there, we'd also get HCl. A bromine on there, we get HBr. But normally, I'm not going to throw those other things on there. Normally, this is what you have. Doesn't matter the backbone, it doesn't matter the branching, nothing. It goes to, and notice I haven't balanced the equation either. The balance that I will have to have 1, 2, 3, 4, 5, 6 carbons. That means 6 carbon oxides. We have to count the H's to appropriate them. Okay, what if we, instead of sparking it, we oxidized it instead? So whenever we oxidize anything, we have to determine whether it's primary, secondary, or tertiary. So what's this one? Primary. Now, the important thing about primary is we have two hydrogens there. So if we have 2 hydrogens on the carbon hydroxyl group, we can oxidize it twice. So the first time we oxidize, we get an aldehyde. That forms an alcohol. And this is where, let's put a blue dot there. And then next to that is hydrogen. Now we can If we don't isolate it, it will continue to oxidize because of that hydrogen on that carbonyl on the end.
So when it comes to drawing products, like how you just drew aldehyde and how on the last one you drew a ketone, how did you know how to draw that specific structure? Is it all the same regardless on the reaction?
It's where the OH is attached. Everything revolves around that. We're going to see in the next unit, we're going to have something called an anomeric carbon. Same thing. Everything goes around that particular carbon. So the carbon that the OH is attached, you count the hydrogens there. Okay, if there's just one hydrogen there, you go to a ketone. If there are two, like a primary alcohol, you can oxidize it twice. But it's the carbon that's attached to the OH. Okay, so the next thing we're going to do, we're going to continue the oxidation. Now we create an acid, carboxylic acid, which is a unit 3 functional group. So on your diagram, your flow chart, just follow it on down. It'll show, if you start with a primary alcohol, it'll be 2 oxidations, and it'll show you 2 steps, and then it'll label it as an acid. Intermediate, it only oxidizes once, and it's primary alcohol. You stop at the aldehyde. But it's hard to do that because aldehydes are not all that stable. And what happens is it's more stable if it's oxidized more. So I'm going to, as a, like with ethanol, when you oxidize it, goes to the aldehyde. So we go aldehyde, acid. In this case, it's acetic acid, and this would be primary alcohol. And this is what happens in your liver when you drink. Drinking alcohol, your liver oxidizes it with something called alcohol dehydrogenase. Assuming you have the right enzyme, it kicks it over the acid, and you pee out acetic acid. Now, when you take a breathalyzer test, for whatever reason, it's not done with enzyme. It's done with oxidizing agent. And it changes color when what ethanol you have. And there's a specific color that corresponds to the legal limit of alcohol. If it's darker than that, off we go. Tow your car the whole bit. If it's lighter than that color, they'll say, just drive carefully, sir. And don't drink. And you're fucked. Okay. Okay, label the following alcohols: primary, secondary, tertiary. Okay, so we have how many? Now this is going to be the carbon the OH is attached to. Okay, so how many hydrogens are on the first one? On that carbon that the OH is attached to? None. The OH carbon, or the OH hydrogen doesn't count. It's the hydrogens coming off of the carbon. So that means that's a tertiary or 3rd degree. Okay, on this one here, that's the carbon that the OH is attached to, so how many hydrogens are there? One. Okay, that means that's a primary. Okay, so when you're drawing benzene structures, you have the benzene in the middle. Okay, it says diethylbenzene. It means two ethyl groups are branches off the benzene. Okay, so we have three structures: ortho, para, and meta. Ortho is the right together. Let's do that as ortho. Para means they're across from one another. And meta means they're one apart. So people used to use orthodichlorobenzene as a moth repellent. They don't use that anymore because it's a chlorinated hydrocarbon. So that's what it would look like from the far away. Now, what is another name for the same structures? Okay. So this way we're going to number them instead of saying ortho, para, meta. Okay, so you can name them either way. Unless our test and say name them two ways. In the numbering system, based on benzene ring. Now, if we have a functional group on the benzene ring, that automatically makes that carbon number one. And here we just have hydrogen. So you can choose any hydrogen or any carbon you want. Name it from there. Okay, now this is a two-step reaction. Yeah.
You go over what the three cases mean, so ortho, meta, and para.
Ortho, right together. Para, think of a paraglider, wings out like this. I mean, they're totally opposite. And then meta is in between.
Thank you.
That's the way I remember it. Okay, so here we have an alcohol. Okay, and we're going to throw in some acid and water. What are you going to make? Okay, so we have an alcohol, excuse me, an alkene. We throw in water and an acid, we end up with an alcohol. So that means the water is going to be across here. And there. So we're going to end up with two alcohols. And they're not the same either. So here is the damn it. Where did the other one go? Right there. Let's start over. Come on, I got overlapping pages there. That's going to be goofy. So we're starting with water and an acid. Okay. And that gives us a mixture. So there's an OH on either side of that double bond. Okay. That's the mixture. Then we quickly oxidize it again. That page disappeared. Okay, I think it was oxidizing. So let's then take this and oxidize it. So we're going to oxidize an alcohol. We have to determine what issue, primary, secondary, tertiary. So this guy is secondary. Okay, so secondary alcohol forms a ketone. Okay, so that's the mixture you get. I get a cyclic ketone. Oxidized secondary alcohol. Now with this test, last one was okay. We skipped over naming, so let's. Okay, so we're gonna start. Okay, so we've got heptene. So that's going to be 7 carbon backbone with the double bond between 3 and 4. And it's trans. So whenever you see trans, trans is a normal looking backbone. This is where it's kinked. Okay, so let's draw a 7 carbon backbone. Okay, carbon 3 is where the double bond starts. And then we have 3, 4. Oops. Dimethyl. Now, if this said cis, so this is trans, it would be like this. Remember, cis is like sisters. Those are the ones that are together. Trans is the opposite. Okay, so our backbone is 5 carbons, and it's an alcohol. Carbon number 3 is the OH carbon. And we have 2 and 3 methyl groups. Okay, this we're starting with a phenol, which is the benzene ring with an OH group. And the phenol automatically makes that carbon number 1. So we have 1, 2, 3, 4. Now, as an alternate, we could number the other way. So we have 3, 4. Same structure. It wouldn't matter which way you went. Okay. Cyclohexanol. Two propyl. Because this an alcohol automatically becomes carbon number 1. Oops, I goofed up. Okay, so we have 2 propyl and 3 methyl. Okay, what's wrong with the following chemical name? Well, let's draw it out the way it says to start with. Okay, the backbone is four carbons, and it's an alkene. Okay, so we go 1, 2, 3, 4. And it says 2 butene, so that means it's going to be this, and 3 butyl. 1, 2, 3. I might keep wanting to. Okay, that's the way I just followed that incorrect naming. That's the molecule I ended up with. So tell me what's wrong with the name based on that molecule. That's the idea here. Well, we start with what when you name something? Backbone. So let's look at the backbone here. So we've got 1, 2, 3, 4, 5, 6, 7. The backbone. Remember, it's got to go through the double bond because that's the functional group. Okay, so let's start with heptane. And it's an alkene, so it's going to be heptene. And then we have a methyl group on carbon number 1, 2, 3. So it's 3-methyl heptene. Everyone see why that's wrong? And lastly, yeah. The one I just did this one here. Okay. So am I okay? Well, I'm human. I make errors.
I just have to make sure that I can write it
Oh, okay. Does that make sense what we wrote? Okay. Okay, so I frequently will have a question like this. I give you some structures. Name the electric forces. Okay, first of all, is there an oxygen present? Boom. Are the other ones have an oxygen present? Yeah, the first and third one does. So, if you have an oxygen with an H attached, it's hydrogen bonding. And then we have other dipoles. And then we always have London dispersion forces, LDS. Okay? And that's ascending order of strength. LDF is weakest, hydrogen bonding strongest. With this guy here. Well, it's just an alkane, so it's LDF only. And then the last one we got, well, we always have LDF. And we've got dipole. Now, the oxygen has three options. How is it attached to a carbon? Well, we have one attachment to a carbon, and we have another attachment to a carbon. So that's not hydrogen bonding because hydrogen is not bonding to the carbon, to the oxygen. Carbon is. So those are all dipoles. Okay, so which of these has the strongest IMF? First one, hydrogen bonding is the strongest. The next one down is we have oxygen there with an ether. Those can be next. And then lastly is the cyclohexane, which is very nonpolar, or the lowest IMF, just LDF only. Now the next question asks, now rank them in terms of boiling point. The higher the IMF, higher boiling point, no exceptions. So it's going to be number one, highest, number two, and kind of in the middle, and number three. This is where boiling points. That's the second part of the question. Now it says, why doesn't diethyl ether undergo hydrogen bonding? Well, what does diethyl ether look like? Well, we've got an oxygen and an ether. Why doesn't it undergo hydrogen bonding? What is required with hydrogen bonding? H and what?
The oxygen.
H and O, hydrogen and oxygen. You see a hydrogen and oxygen attached here? The carbon attached, carbon attached. That's why it doesn't undergo hydrogen bonding. By definition, hydrogen bonding is so nitrogen, oxygen, fluorine. We never consider fluorine in the human body. It's not natural. Even though we add it to our drinking water, it's not natural. Okay, and then there's one more part here to go. Name these guys. Okay. So this is based on phenol. So that would be carbon number one. Carbon number two, we have what? Not a methyl, ethyl, propyl, butyl. Butyl has how many carbons? 4. 1, 2, 3. Propyl, That's 2-propyl-phenol. Okay. So we establish backbone again. Let's see, we can go 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this guy in the beginning doesn't count. So which of the backbones has the functional group on it? Yellow or pink?
Is it me?
Pink. And yellow is just as long, except it doesn't have a functional group on it. So we're going to use the pink one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's a deca, and it's an alcohol. So it's a decanol. And we have a branch at carbon number 1, 2, 3, and 4, 5, 6, 7. So we have a branch, an ethyl branch at, what is it? 3 and 7. Then I want to emphasize, you've got to have a functional group on the backbone. Okay. So we have, this is a pretty straightforward one. Got no branching. We got 1, 2, 3, 4, 5, 6. So it's a hexene. And where is the double bond start? From a number 2. Well, one more problem to go. Okay, let's go to the backbone. Now the double bond is in there. We have to include that on the backbone. No choice. One, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so it's 6. So it's a hexene then. And we have a carbon, we have a methyl branch on carbon 1, 2, 3, and 4. Right? 1, 2, 3, we have 4. Okay, so we have 3,4-dimethyl hexene. And we be done. This concludes unit 1. Finish your dry life. An excellent way to study for this test, number 1. Number 2, study the practice test. Study the practice test. My test will be the same format as practice test. Now, if I was a student, I wouldn't want me throwing in trick questions. I don't like trick questions when I was a student. So as a professor, I get to decide whether I include trick questions or not. Now, it may appear trick to you, but it wasn't intended to be a trick question. Let's see. If you're not in a study group, I highly recommend trying to get in one. Study groups are very efficient in improving test scores. There's a lot of, you need in this building, you need over in natural science building, a lot of places to move. You need Zoom session as well. But if you're not in a study group and want to be in a study group, message the class. In Canada. You also message individuals in the class as well. Okay. Any questions about anything in general? We have fun. Usually I get some questions. See how valuable it is to be in person rather than the video.
Yeah. They're the person.
I like in-person lectures too. I like people.